All right, guys, our last section in the chapter. So our last section is something that we've already been working with in class, and it's talking about graphs. So talking about using the scientific method to answer questions after we collect that data, as we've already seen in some of the labs that we've done. It's so nice to take that data and put it into picture form because it makes a lot more sense when you look at it in picture form. So chapter 2, section 4 talks about graphs. So graphs are actually a type of a mathematical model. Definition of a graph is a picture that shows how two variables are related. So we're taking two things in our experiments that we test and we are putting them into picture form. And the two things that we're putting into the experiment are our dependent and independent variables. And we have talked about these a little bit for the labs that we've done. This picture on the slide here talks about flow rates of common objects. So when we're talking about flow rates, think about water moving. So if you look at the graph here, I can see a drinking fountain has a flow rate of a little less than 50 milliliters per second. And we kind of keep going up there for a while. Highest flow rate, as you can see here, is the non-efficient shower head, which is about 410 milliliters per second, all the way back down to the bucket that would just have sort of like a little spigot on it that you can open on the bottom there. But clearly, just by looking at this graph, I can see what are the two things that are related to each other. It's a different object and then the flow rate. What's the amount of water that's coming out of it? But the picture here shows me essentially what the data is that we collected. It's a lot easier to look at than a data table. So a graph is really just a picture of information. We take that information from our data table that we use in our lab, and now we're going to take that information and then make a graph with it. So graphs are used to display data collected during an experiment. In this particular graph here, it looks like they're comparing the amount of gas that you're going to be using in comparison with how far you can travel in miles. So for this particular car, if you were going, let's say, had 5 gallons of gas, it looks like you could go maybe around 110, 115 miles. You can see in some instances, you really kind of have to do your best with estimating based on just kind of lining things up. It is always a lot easier if you have a ruler and you kind of line things up with a ruler. Even if something is on the computer here, I suggest even just getting like a straight edge and you can use that. It works a lot easier. So this is a picture of what we call a line graph. You can see there's a line on it right there. Then the question, this one says 10 gallons of gas. So if we do this one quick and I go up 10 gallons of gas, looks like that would be around, I would say, 250 miles. So on our graphs, we graph our independent and dependent variables. And when we look at a graph, we have two different axes on the graph. So the x-axis is the one that's on the bottom. So on the bottom of the graph, it is the horizontal line on the bottom there. So that would be the independent variable. On the other side, it is the dependent variable, or the x-axis. Remember, the dependent variable is the one that changes based on the other one. If you switch these around, your graph will actually look really weird and it won't make any sense. So anytime we are making graphs, it's really important, put on the bottom the independent variable and then the one that changes because of the independent variable on the other side. We measure time a lot in science, and time is an independent variable. It's almost always the independent variable, and you think about why that is. Time is something that isn't affected by anything else. When you watch time go by on a clock, nothing can affect that. It's going to keep going and going and going. So if we are graphing time, which this graph is not, but if we're graphing time, it usually is on the bottom. So we have different types of graphs that we can use. These are the three biggest types of graphs: line graphs, bar graphs, and pie graphs. We use different graphs based on what type of data that we collect. If we collect both quantitative sets of data, so remember, quantitative data is data in the form of numbers. So if you collect two sets of numbers, you would use a line graph. So that would be like amount of gas, distance you travel. Both of those are numbers. So if you only have numbers, use a line graph. If I collect data and one of them is non-numerical data or qualitative data and the other one is quantitative data, then you're going to use a bar graph. This is very similar to what we do in the paper towel lab. Brands of paper towel on the bottom, milliliters of water absorbed on the side. So numbers, not numbers, we're going to use a bar graph. Pie graph, anytime we're dealing with percents, pie graphs are wonderful because we can look at the part per whole that we're looking at. So this particular pie graph is the percent a person uses, time used in 24-hour period. You can really quickly see that the brown and the blue are the biggest things. So you can really easily say that person spends a majority of their time sleeping and at school. When we make graphs, it's really important to have everything labeled so people know what they're looking at. So graphs should always include a title on the very top. When we do labs in class, we just often pick the title of the lab. So like quicker, picker, upper lab, the double stuffed lab, those things go on the top. Then on the axis, on each axis, you want to do a couple of things. You want to make sure that you have the numbers labeled so you can see, like on this particular graph, it's the X value range. But then you should also say it's not just time washing cars. We need to always have a unit attached to it because time washing cars, maybe that's minutes, maybe it's seconds. So it's very important to include units. And they did the same thing on the Y-axis. So if I see the amount of money in the cash box, I can see that's in dollars. So it would be $20, $40, $60. So you need to make sure you have a title. You need to make sure each axis is labeled, the numbers are labeled, and you always include units. Always include units so the person who's looking at your graph knows what that means. Now we rely a lot on applications to make our graphs now, but just to give you a little bit of an idea, if we ever do have to make one on paper here, it's really simple on graph paper. You're just going to take a ruler, you draw each of the axes. Remember on the bottom it's the X, the one going up and down is the Y. The independent variable is always going to be on the bottom on the X-axis, and the dependent variable, so one that's changes based on the other one, goes on the Y-axis. So if you look at this one, this is a car wash. When you think about this, time washing cars is not affected by how much money is in the cash box. How much money is in the cash box depends upon what time it is or has gone on in that. Then we always make a scale. Now there is a numerical way to do that. You take what is your total data range and divide it by the number of boxes that you have. So let's say your range was 20 and you had 10 boxes, 20 divided by 10, every box would be worth 2. You can use a pencil. I would always use a pencil in case maybe your math is off a little bit or something, but you mark it out if you're good to go. Our whole goal is when we're making graphs is they should be spread out. You shouldn't be just using one corner, tiny corner of a graph. You want to take that data and spread it out to get the best picture possible. So your book walks you through an example of one that they do here and the value that they would have per box. So take the total range divided by the number of boxes, and that gives you the value per box. That's all you do. When you were given the data points from the data table, you plot them so that you take the two numbers, where do they cross up? So let's say it was at 0 and 0, that's where that point's gonna go. Maybe my next one is at 1 and about 32. So they had about $32 in the cash box at 1 hour time. At 2 hour time, let's say they had 40, so that's where it is. So you see what we do there? You find it on the bottom. Where does it match up? That's where your point goes. Where is it at the bottom? Where does it line up on the left? Then you just take and draw a line through it. Title for the graph, and then this one's good. It looks like everything is labeled. I have units and everything is labeled on there. So graphs are just simply a tool that we use in science to help us take that data that we collect in experiments and see a picture of it.